Okay, so let's start by recapping the algorithm for canonical quantization that we learned in the last class. Today's topic will be we will quantize a free scalar field theory. And so the algorithm is, first of all, how do we go from a classical field theory to quantum? Let's quickly recap. We start with the Lagrangian density, which is a function of the field and its space and time derivatives, which is what I mean by mu equals to 0, 1, 2, 3, 4. So all the del phi del x naught to del phi del x 1, all the space and time derivatives are here. And then we define the conjugate momentum to the field, and here in the definition only the time derivative of the field enters here. So pi is equal to del L del phi dot, where phi dot is the time derivative. Then we find the Hamiltonian density, usual formula just like in the quantum mechanics case, and the Hamiltonian density will be now a function of pi, phi and the space derivatives of the field. So because the time derivative will be related to pi, when you make this definition and make this switch, phi dot will disappear from the formula, just like in the classical mechanics case. Q dot disappears and you only get P and Q. Similarly, here you will get pi and phi, but also this space derivatives will remain. And then you there is some Q here. Then you demand that you make this into, when you go from classical to quantum field theory, all you have to do is make this phi and pi as operators. These are your basic operators. These are the operators on which all the other operators will be built. So make pi and phi into operators which satisfy the canonical quantization, this canonical commutation relation, and that is why it's called canonical quantization, because you impose this commutation relation. And the final step is find the Hamiltonian for the quantum theory. What is the Hamiltonian density? Just take the function of h, which will be some the classical thing, which will be some function of pi, phi and the space derivatives, and turn it into the same function, write the same function, but of the quantum operators. So this is also here, like this. Okay. So this is the algorithm to go from classical field theory to quantum field theory. Now there's a shortcut way which we had done first of doing the same thing, which is instead of doing all of this, you could just start with the field, take a Fourier expansion of the field, and then you get a infinite number of harmonic oscillators, and then you just quantize each harmonic oscillator. Either way you do it, you get the same result. So doing these two things are equivalent, and you can think of doing it this way as a shortcut method of achieving canonical quantization, where you don't go through all the steps, but it's the same answers. I mean, these two things are the same thing. Okay, so I will pause now for questions.
Sorry, is it like saying in quantum mechanics we can expand in a vector based on the basis vectors? Is quantum field theory equal to saying that?
Yeah, it is. It is very much similar to that, where you expand something in quantum mechanics, you can expand something in a basis, and it is kind of similar to that because we will see in what sense this forms a basis.
Like
but
in quantum field theory, you expand in terms of fields.
Yes. In quantum field theory, we expand in terms of fields. Yes. Okay. And any other questions? Okay. So let's now take our first field theory and quantize it. I mean, we have already done the string, but that did not have any particular physical relevance for quantum theory. Now we will take a free scalar field. What do you mean scalar? The field is a scalar. So you can have a field that is a scalar, you can have a field that is a 4 vector, like the magnetic vector potential that I showed you earlier could be written as a 4 vector, as the electric potential and the magnetic potential. And if you were there in the GR class, you have seen a tensor field also, which is the metric G mu nu. It's also a field. It also can be quantized, although no one has managed it yet. And we deal with the simplest possible case, free scalar. So in nature there is an example of a scalar field, which is the Higgs field, for example. And all these other fields, electromagnetic field, and then we have the field for strong and weak forces, which are kind of similar to these vector fields. These are also vector fields. And gravity is a tensor field. So we take this. And we have this word here, free. What does free mean? Free means non-interacting. So this means there is no, first of all, the simplest thing that we will start with is one where there is no interaction. And then later we will try to understand interactions. But this is non-interacting. So how to see it is non-interacting will not be clear right away from the formulation, from the equation. But as we study this field, we will realize what do we mean by interaction, who is interacting with who, and why this is non-interacting. Let's start with the equation. So for a scalar, the simplest and the only quadratic equation that you can write for a free field is the Klein-Gordon equation, relativistic and second order. So this is a relative, higher order equations are the problem. So we want a relativistic equation for a scalar, and the simplest one is given by the Klein-Gordon equation. So this is the Klein-Gordon equation that I have written here. Eta mu nu del mu del x nu del x nu minus m square. And the same thing we will write in this notation, del mu phi minus m square phi is equal to 0. Remember the notations we talked about? These two things are the same thing written in different notation. So this means this. And what is this? So let's, for one time, let's write this explicitly. So here there is a by Einstein summation convention, there is a sum over the repeated indices mu and nu. So I will put mu and nu. If I put mu and nu everywhere, this is eta 0 0 del phi. Mu is 0, nu is 0, del phi del x 0 plus, remember eta mu nu is this matrix. So the only non-zero elements are when mu and nu are the same, the diagonal elements. So 0 0 1 1 2 2 3 3, these are the elements. So this is plus eta 1 1 del phi 1 eta 2. Square minus m square phi is 0, and this is minus 1 square. This is 1, and then I can write this as square. This is 1. Okay. So this is really the equation that we are looking at here, as you all knew already. Okay. So now we want to quantize the theory. So first let's take our usual shortcut method and try to decompose this theory into Fourier modes. So start with the field, take a Fourier expansion, and now substitute this in the equation of motion, okay, which is this. So how do we do this? So first let's say we want del phi del x naught square. So that is, oh sorry, my bad, this is wrong actually. Someone has to tell me these things. This is not the equation. See, sorry. This is del 2 phi mu del x mu del x mu. This is the equation. It's a second order equation. Okay, so this means this is really minus del 2 phi del x naught 2 plus del 2 phi del x 1 square equal to 0. Okay. Sorry, that was my mistake. This is the equation, minus x square. Okay. So now, for example, let's take derivatives here. So first of all, del 2 phi del x naught 2, and here you can see that the only time dependence is in this phi k part, and so this will become del 2 phi k del x naught 2. Okay. And what about del 2 phi del x 1 square? So this is d3k 2 pi cube, and now phi k does not have any x dependence, so phi k remains as it is, and this is del 2 del x1 square of e to the power I kx. So let me write this, del 2 del x2 of e to the power I. K dot x is what? It is k1 x1 plus k2 x2 plus k3 x3, right? And then when we want to do this derivative, what do we get? So this is with x1, so it will only act with this, and the first derivative will bring down a ik1. So this is equal to del x1 of acting on this whole thing. This will be I k1 e to the power I k1 x1 dot dot dot, right? And then the second one acts, again it goes through, acts here and brings another factor of ik down. So I get ik into ik is minus k square e to the power I. So I get this whole thing minus ik dot x into phi k into t3k by 2 pi cube k1 square. And similarly for all of these, right? For all of these, for each of these, x2, x3, each of these. So what will be the final upshot? For a moment. So the final upshot will be, I get a equation d3k by 2 pi. We have already done the one-dimensional version of this, but now we are doing in 3 dimensions. And we have e to the power I k dot x from this term, first term, which was minus del 2 phi del x2, we get this. So this is minus del 2 phi k del x naught square, and I get plus minus k1 square minus k2 square minus k3 square into phi k del 3k 2 pi cube, and also e to the power I k dot x also here. So I can take that in common and I get d3k 2 pi cube e to the power I k dot x into del 2 phi k. This is really time, so let me write this as t plus mod k whole square, sorry, yes, minus sign outside, mod k whole square into phi k equal equals 0, because k1 square, k2 square, k3 square, k being a vector is just the modulus of square. Okay, and so then we have a equation for a harmonic oscillator with this. But what we have done here is we did not consider the m term, right? We forgot about it because I forgot about it. So this is the correct equation for a massless scalar field where there is no mass, m is equal to 0. But now if I plug back the m, everything will be the same except instead of k square you will get another term here which is k square minus m square. Okay, so let me clear some space.
This mass is the mass of the field.
This mass is some mass we are associating with the field. Yes, so with the field we are associating some mass. What is the meaning of this mass? We will see that when we understand particles from this field, those particles will have that mass. So it will be the mass of the particles. Taking up more space than I meant to. Oops. So this is for, so the equation for the massless case is this. This is massless, and when we have a massive scalar, we have k2 minus plus k square minus m square 5k equals 0. This is massive. Okay, so again we have that we have reduced this system into a set of infinite harmonic oscillators, and now we can quantize each harmonic oscillator like we have seen previously. So again let me move some things. So once we have infinite harmonic oscillators, all we have to do is quantize each harmonic. So we see that the modes, each individual mode in this phi k field also satisfies, just like the string satisfies, a harmonic oscillator equation where this is your omega k, this is your frequency, harmonic oscillator frequency, and it varies from one to the other. It varies from each mode. So for different modes there is different frequency. Again, just like the case of the string. So this is, each of them satisfies the harmonic oscillator equation, and therefore we have what do we have? We have that we can quantize each harmonic oscillator like before. So we make them, each harmonic oscillator, into an operator, and each operator, then we can introduce this ladder operators, creation and annihilation operators, where we demand that each of them have a commutation relation which is equal to prime dagger is the same as delta. This is how I was writing till last time, because this is again a continuous index, but I was cavalier about conventions, and so from now on we will follow this convention where there is a 2 pi cube over here. Okay, this depends on how we define our Fourier transforms, and the way we are defining it we have to use this 2 pi cube here. Okay, this just comes from using a certain convention, and all the other commutations are 0. Prime is 0, and similarly for daggers, prime dagger is 0. So this just says that for a given when k and k prime are the same, that's when we are talking about the same harmonic oscillator, and that's when these two don't commute. Otherwise, they will always commute because they're just different harmonic oscillators. We also see a sense of why this is called a non-interacting theory, because this decomposes into harmonic oscillators which are not coupled, which are not interacting with each other. So it's a set of decoupled harmonic oscillators which are just oscillating on their own and not interacting with each other. They are not chained to each other. There is no coupling. So this is a simply free uncoupled harmonic oscillator. So this becomes free field theory is equivalent to uncoupled harmonic oscillators. Okay, so now let me pause for questions before we do the same thing with the longer algorithm that I wrote down previously. Okay, so you see how this defines a quantum theory, right? Because now I have these operators. So this system is just a system of infinite harmonic oscillators, and we know how to define the vacuum for such a system. That is the state where all the k, this is 0 for all k. This is the lowest energy state. So this is the one that is sent to 0 by the annihilation operator, or the whatever you call it, the ladder operator of all the harmonic oscillators. So that's the one which is the lowest energy state for all k. And then by acting on this A dagger case on all kinds of A dagger case on this ground state, you can build up all the states of this system. So there is something we again covered for the string, and we will again cover this for the scalar field theory in the next class. But what should be clear from this, that this is now a quantum theory with the ground state and with all the kinds of states in the Hilbert space, which you can define by acting on this with some operators. Okay. So questions? Okay. So let me proceed with the longer algorithm. So now what we have to do, we have to start from the Lagrangian, which is this, and the simplest case you can consider is in 2 dimensions, where the Lagrangian, explicitly writing the Lagrangian, just looks like this. Okay, minus del phi del plus del phi del. This is in 2 dimensions. So this is the Lagrangian, and you can check that this is the correct Lagrangian, that this is the Lagrangian that produces the equation of motion that I gave you. So let's check that. Okay, just as an aside, let's quickly check that this Lagrangian produces the Klein-Gordon equation. Okay, so what is the Lagrange equation of motion? It is this that we had written up before, and explicitly, if I turn all the mu's into, we have here time and space, t and x, I get, so this del mu, first take it as t, then I get this term del del t of del l, del phi del t, and with x, del x, del phi del x, minus del phi is equal to 0. The difference between this and a classical mechanics system would be that this term would be still there, this term would be still there in mechanics, this second term would not be there, but in a field theory, this second term is there. Okay, so let's evaluate first del L, del of del phi del t. So what is that? If I take derivative of this with respect to del phi del t, what will be the term I get here? Okay, I'm expecting someone from you to answer this one.
Minus 2 del phi by del t.
Yes, very good. So minus 2 del phi del t, and then I take del t of this, then I get del t of minus 2 del phi del t, which is simply minus 2 d2 phi dt2. So there's a half here, which I forgot to write here, half of this, and so this is just minus del t phi del t2. And so similarly del phi del x would be just 2, because there is a symmetry between del phi del t and del phi del, almost the same, just it's changing sign, and this 2 also gets cancelled because of this factor, and I get del t phi del x2, and del L del phi, what is del L del phi?
2m square.
Yes, this is 2m square phi, and there's a half outside, so it is m square phi, and so I get finally minus del 2 phi del t2 plus del 2 phi del x2 minus m square phi is 0, which was the same equation, Klein-Gordon equation that we started with, that we had written down. If we scroll up, we will see the same equation again. And this we did just for simplicity, we did for 1 plus 1 dimension. You could have del phi del y del phi del z terms, and that will give you the full 3 plus 1 dimensional Klein-Gordon equation. Okay, so what is pi, which is the conjugate momentum del phi dot? We already calculated it here, right? This is pi, so this is minus del phi del t, and then you can the classical Hamiltonian density, you can write it down. Did I write it down somewhere? Probably not, but this will be simply pi is minus del phi del t, so you can replace that, and so you will get, let me just write down the final result. So that this del phi del t square minus del phi del t square becomes pi square, and you will finally get the final term will be pi square. This will remain and this will remain, so you will get pi square plus del phi del x square plus m square phi square, and this is in 1 plus 1 dimensions, there is one space and one time, and in 3 plus 1 dimension is the same, except now we have 3 derivatives, del phi del x, del phi del y, del phi del z. So square of all of those, meaning the square of the, not Laplacian, because Laplacian second derivative, this is the square of the gradient, phi square plus m square phi square. Okay. Okay. So now to go to the quantum theory, all we have to do is impose this canonical quantization relation. So now I make phi and pi into operators, and I demand that they satisfy this. And then I will have to write the Hamiltonian in this form, and then I will define quantum theory. Okay. But now what we want to check is that these two kinds of ways of doing things, the shortcut method and the longer method, are the same. Meaning that if I just decompose this into harmonic oscillators, then I will get the same answer. It's the same thing, it's the same theory. And the simple way to see that is take these fields now after quantizing them and decompose them into, now take a Fourier transform and then rewrite this in terms of some operators ak and ak dagger. Some operators ak and ak dagger. We can always do that. We can always define phi k as a sum of some ak and ak dagger operators and get a term like this. Similarly, pi x like this. This is the same kind of relation we had written down previously here for phi k. So if you just make this replacement for phi k and phi k, here you will get these terms. Now all we want to check is that these commutation relations that we imposed are equivalent to these. Okay. So the commutation relations we have now in this longer method, phi is 0 and similar for pi. This commutes with itself always, and similarly these guys also commute for always. Okay. So remember, in the shortcut method we are saying let's take this set of harmonic oscillators and let me quantize each of them. And here we are not saying that. We are saying that let me take the field and let me directly make the field into an operator. But taking the field into an operator and then decomposing them, what we get are again a set of harmonic oscillators. How do we see that? We see that by saying that if I take this set of commutation relations, then this will follow, or if I take this, then this will follow. You can prove one from the other. If you assume this, if you take this decomposition and assume that AK and AK dagger follow this commutation relation, then you can prove this one. And if you assume this one and then take the decomposition, then you can prove that AK and AK dagger follow that commutation. So let me write the logic here. Phi x. So I can either start from AK dagger commutation relations. I can either start from this del k minus k prime, okay, and then from this I can prove that phi x prime is I del cube x minus x prime, or I can assume this is true and then taking the decomposition, then writing phi and pi like this, then I can show that A and A dagger must have the commutation relation satisfied by ladder operators in the harmonic oscillator. Is this logic clear, or should I explain this more? Seems unclear. Everyone seems like not comfortable with this. Okay. So you agree that I can take some operator and I can always Fourier transform it. You will also agree that for any operator phi k, and similarly I take this pi k and so I take phi k, I Fourier transform it. I take phi x, I Fourier transform it. Pi k to pi k x, and I get two operators phi k and pi k, and then I define let me go to the end and do this. This is phi and pi, and then I say, okay, let me define two new operators, AK and AK dagger, which are combinations of this, some particular combination of this phi k and pi k up to some. This is AK dagger. I'm not writing the exact thing, so just something like this, phi k minus I pi. At this point, these operators do not have any what do I say? Do not have any interpretation in terms of ladder operators so far. All we know is that this big pi, they satisfy the canonical commutation relations. Because suppose I have started with that. I have followed the algorithm, I have quantized, and I know that I have imposed this relation. And then I define these two random operators by Fourier transforming and taking this. At this point, I cannot say what is, do they have an interpretation in terms of ladder operators? We don't know. Only if I take the commutation relation between them and I happen to find that they have a relation like this, then I can guess, then I can kind of make that claim that okay, these look like now the ladder operators for harmonic oscillator. I would also need the Hamiltonian, but that comes later. But at least they satisfy the first check of a ladder operator of a harmonic oscillator. So suppose I started in this path, I did not do the harmonic oscillator decomposition at all at any step, only after taking this Fourier transform, defining these two operators in this way, and I find that this is true, then I can say okay, I could have also done this other way, where I first decompose the fields into this before quantizing, and then I take every AK and AK dagger, every coefficient in the expansion, and turn them into operators. Then that would have given me the same set of same quantum theory, same set of operators. Okay. So one algorithm is start from phi and pi, make them into operators, and then check that if I decompose them into some terms like this, then these terms, then these operators that appear here satisfy the commutation relation. And the other goal was start with classical phi and pi, write them classically into Fourier transforms, take the classical phi k and write it as sum of some coefficients ak plus ak star, make these into operators which satisfy the ladder operator relation, and then say this is my quantum theory, and then I can go back and check that now that these are operators, then phi k are also operators and phi pi are also operators, and what is the commutation relation satisfied by phi pi, and then you will see that it's the same thing. So these two ways of doing things are really the same. Okay, so now we check that they are the same, and this is I think the last. We will not have time to do the Hamiltonian today. Anyway, we will do the Hamiltonian in a tutorial. Okay, so let's check that they are equivalent. So we will start with this and we will prove this one. So we will assume that this is true. We will assume that the harmonic oscillator commutations are true, and we will prove from them that phi and pi follow. And you can go the other way around also. And this is, we will do an example of a field theory calculation which is full of algebra. So this will be a little bit, but to learn field theory you have to get used to some difficult, some little bit tedious algebra like this, because in field theory you get the physical insights and understanding only after you go through some suffering in the form of algebra. So there's some unavoidable suffering involved in learning field theory, which we do now. Okay, so we have to show that this is, we assume this and we have to show what is this. So let's write phi x carefully. Let me call this d3k 2 pi cube. What is the formula? It's square root of 2 omega k. Remember, omega was k square minus k square plus m square, and then I have ak e to the power, let me check, I k dot x plus ak dagger e to the power minus I k dot x, and then pi at a different point y, and we should name the dummy variable something different also, otherwise we will get confused. So let me call it p, and this I here, and this is square root 2 omega p, you can say square root of omega p by 2 a p into the power I p dot x y minus a p dagger e to the power minus I p dot y. Okay. Now make them take the commutation relation. Okay, so I have to take the commutation relation of this operator with this operator. So I have to take by 2 pi cube. This whole thing, why am I writing? And I have good. So now, of course, we can take the integrals outside. And we have k dot x plus k dagger to minus I k dot x ap p dot y minus ap dagger to minus I p dot y. Okay. So which of these operators commute? Which of these operators will give non-zero commutations? What is the commutation between AK and AP? Is 0 because they are both A. And what about A dagger K and AP dagger? Also 0. So this is omega P by omega K, everything outside. And the only non-zero terms here are AK with AP dagger, because one is A and one is A dagger. So I have minus AK, minus coming from here, AP dagger. AK is multiplied by e to the power I k dot x, and this is minus p dot y. So this term coming from these two terms. Okay. And there will be another term which is coming from these two terms, which is plus AK dagger AP e to the power I minus k dot x plus p dot y. Okay, everyone with me so far? Okay, now what is AKAP? We know AKAP, the A dagger is 2 pi cube delta k minus p. And so we have here k, oh there was I somewhere, there was I here. D3k, D3p, 2 pi to the 6, sorry. There are two 2 pi cubes here and here. Pi to the 6 square root of omega p by omega k I multiplied by 2 pi cube delta k minus p. So minus sign here, e to the power I k dot x minus p dot y. Okay, try to stay with AK dagger AP here. What is this? This is minus again. So just take the minus outside, 2 pi cube, and I have again, and these are all three-dimensional delta functions. Let me just write a 3 here. And again, this is same thing, k minus p, and this has e to the power minus I, sorry, e to the power I minus k dot x plus p dot y. There's some problem with the minus sign I'm seeing. Some extra minus sign somewhere. Anyway, I will get the answer up to a minus sign, I think, for some reason. Was there a minus I somewhere? Oh, see, this was a minus I here, which I missed. So let me put, there was a minus I. So this is minus I. This is minus I. This is minus I. This is minus I. Yeah. Okay. Sorry. Okay. Minus I. 2 pi cube cancels with 2 pi to the power 6. Let me just 2 pi cube here. And now, this is the fun part. We have a delta function. Okay, so we can integrate. So we know d3k del cube k minus p into some function of, let's say, p. We can replace, this will become what? This is f of k. So we can use this to integrate over, let's say, p. And so then once we have integrated over p, this goes away and we are, all the k's become p because of the delta function, this formula. Wherever we have k, wherever we have p, we replace it by k. So omega p becomes omega k, and here we have minus 2 pi cube e to the power I k dot x minus this term becomes, someone should say it.
Wouldn't in that Dirac delta function we would have fk, and when we integrate over the, in the variant that you have written down that.
This formula,
No, I can't see your pen on the screen. I'm just saying the.
this formula.
Yes.
Huh.
So I'm just saying that it should be fk, right? So when you integrate over.
Oh, I'm sorry. Let me say this. P. Okay. So let's integrate over P. Okay. So here also we are integrating over P. So we have integrated over P, and then what about this term? What would this term become? After the integration, I have it to I k dot x minus k dot y. So all the p's are going to be replaced by k's. Similarly, the next term is, so this is minus over here, plus 2 pi cube e to the power I minus k dot x plus k dot y. Again, p is replaced by k, right? Because I have integrated over the delta function. And so putting everything together, I have d3k by 2 pi cube. Now omega k cancel out in this term here, and I have minus I into minus sign. So I just have I, and I have 2 pi cube, and I have again there's something, there's a factor of 2 from somewhere which I have missed. Oh, I'm sorry. See, there was a square root of omega p by 2 here and a 1 by 2 omega k. So there was a square root of 2 from here and a square root of 2 from here. That gives me a 1 by 2. So there's a 2 here, there's a 2 here, there's a 2 here, there's a 2 here. Okay. Now we have here e to the power I k dot x. Now I can take k in common, k dot x minus y, and this one is equal to minus I k dot x minus y. Okay, this is what we have. Now, this 2 pi cube, no, this 2 pi cube is no longer there, already cancelled. So I have I, and let me take all this outside. 2 pi cube. I have d3k e to the power I k dot x minus y plus d3k e to the power minus I k dot x minus y. Now what I can do is, it's easy to see that these two integrals are actually one and the same. And the way to see it is you can take change of dummy variables. You take k goes to minus k. If you take k goes to minus k, then what happens is you start with minus infinity to infinity d3k. When you take k goes to minus k, this is something we did before. This becomes minus d3k, but also these two things flip, because now minus infinity to infinity. The endpoints flip, and then when you put it back by taking another minus sign, you get the same thing. So this whole thing remains the same after taking a minus sign change. Is this clear?
The second step, how would be?
Okay, let me do it for one integral, and then it will be clear. Let's say this is minus. Okay. Now we take this as k goes to minus k. So now this was k is equal to minus infinity and k is equal to infinity. And now when the symbol, when this is minus k, this is minus k equal to k is equal to minus infinity means minus k is infinity, and this is minus k is equal to minus infinity. So these things flip. Is this clear? Right? So I have infinity minus infinity to minus infinity minus dk. But I know that I can flip the signs with another minus sign, right? ab dx is equal to minus ba dx. So I do that. So I get minus of minus infinity minus dk, and so the final thing is minus. This is for 1, and here we have what? We have 3, because there are 3 dk1, dk2, dk3, right? d cube k is nothing but, just like d3x is nothing but dx dy dz, similarly d3k is nothing but dk1, dk2, dk3, the 3 coordinates in the momentum space. And because this is an odd number, all these minus signs will multiply and give you finally another minus sign. And so for each of them you can do this trick and you will get finally the same thing. Actually the part about the odd number is not important. Okay. So when you do this substitution in this term, this becomes, this part as I told you remains the same, but this part becomes k, which is the same term as this one. And so I have these two terms added together, gives me a factor of 2, which cancels with this factor of 2 outside. So I have I 2 pi cube, and 2 of these, so I have 2 d3k e to the power I k dot x minus y. 2 and 2 cancels. I have I 2 pi cube into this integral, which if you remember we did in our first lecture. We said this is nothing but the delta function with the 2 pi cube factor. So we have 2 pi cube and the delta x minus y, and so after all the smoke is cleared, we get the answer we were looking for. Okay. So this is the kind of calculation that you will have to do a lot of when you study field theory. Okay. So we stop here. Next week is of course mid-sem, and we will meet after mid break. So next class will be after mid break, and then we will start with the implications of quantum field theory. So now we know how to quantize it, but after this we'll learn the physics of what. After quantizing, what do we learn about this theory? What is this theory about? And so on. Okay, let's start. Huh?
Is k going to minus k?
Yes.
It's equal to saying that omega is proportional to modulus p, right?
It is equivalent to saying
Omega is proportional to modulus of p.
which omega?
The omega that you take rooted to omega.
This one?
Yeah.
Yes. So in this omega, I mean this last minus k when I am taking, omega is not appearing
That
here.
is true, but
In this part there is no
yeah,
omega.
that is true.
Yes.
But in some test tube they do this flipping of k
Huh.
to get to that form.
Okay. Yes, but in general, of course, omega k is only dependent on modulus of k,
Okay,
so it won't change.
That's the
Yes.
reason why you take it.
Yes, yes. I mean, not in this formula, but in other places you can see that.
Like in
Don't
certain
do
test
that.
tube they do this. I mean,
Okay.
skip that.
Huh.
That should be the reason.
Yeah. So I mean, if you skip in some step like this, then you will need this omega k. When the omega k is around, then you will need this fact to flip. We only did the flipping at a stage where all the omegas got cancelled, so it did not matter. But in other places it can matter.